welcome back. This is section 2 of chapter 2 of Multimedia, Graphics and Image Data Representation. So let us first begin this section by saying that the 8-bit GIF is one of the most important formats because of its historical connection to the web and the HTML markup language as the first image type recognized by net browsers, and that's why we will detail it next. And that also we cannot but to mention JPEG, currently the most important common file format, but as I told you in the beginning of the chapter, we will detail it in a chapter apart. So GIF is a standard. GIF is not only a file format, GIF is a standard that is simple yet contains many common elements. We begin by the 8-bit GIF, which is, as we saw in the data types in section 1, it is 256 color image only, and we have the acceptable color image for the screen, and it is best suited for images with few distinctive colors like graphics and drawings. Of course, if you get married and you want to print your image on the wall, on a big frame, the GIF is not the good format to choose, and neither the good standard, because the data representation in the GIF will not be due to the limit of the bits to represent a pixel, it will not be accurate. So GIF standard supports interlacing. What does it mean, interlacing? It is useful when you have slow internet connection, for example, and you are loading an image. Instead of waiting until all the image data is ready in order to be rendered on your screen, it can be rendered progressively. So this is a successive display of pixels in widely spaced rows. Okay, I will show you the first line, the fourth line, the eighth line, and then I begin to fill in between the lines, and in this way you can have an idea progressively of the content of your image, especially if your image is of high resolution, spatial resolution. So the interlacing supported by the GIF standard is by a 4-pass display process. We will see it next. And GIF is actually GIF does actually come in 2 flavors, the GIF 87A and then the GIF 89A. So the original specification is the 87, and then the later specification came to support simple animation via graphic control extension block in the data, and it provides also simple control over delay time, transparency index, and other things. This is the GIF 87 file format. This is the structure of the file, and this is the standard specification, of course. So how do I read this map? How do I read this schema? I begin with a GIF signature. Every file of following the GIF standard will be beginning by a GIF signature. This is an easy thing. You will see this is the word GIF followed by the version. And then after that you have characters to describe the screen. We call them screen descriptor. They come in a certain way. We will see how. Followed by the global color map. We studied the color map and the lookup tables in section 1. And then you have image descriptor and local color map and raster array, and you repeat. So you repeat this 1 to n times, because a GIF image you can have more than one image inside it. It can be an animation. And finally, to state that this file has finished no more, we have also a GIF terminator. So here is our screen descriptor. We said that the GIF signature is followed directly by a screen descriptor. So let's look inside the screen descriptor. The screen descriptor holds on how many bytes? It holds on 7 bytes, and each bit of these 7 bytes have a signification. So you read them and you decrypt them bit by bit. For example, the first 2 bytes and the next 2 bytes are reserved for the width and height in pixels of the image. Okay, so you read the first 2 bytes, this is the width, and you read the next, after the first 2, the third and fourth byte, it is for the height, and they are stored least significant bit first. Okay. Next, what is the fifth byte? The fifth byte is divided into 3 pixels, then 1 pixel set to 0, and then 3 other pixels, and then 1 pixel, which is M. Okay, let's see what is the first 3 pixel. We say that this number, this is the binary number, plus 1 is the number of bits per pixel in image. So we know here if whether this image is 5 bits per pixel or 8 bits per pixel, or for example 2 bits per pixel, but you have until 8 because you can have 1 1 1, this means the binary 7, and then plus 1, so maximum you can have 8 bits per pixel. This is the information written here. And next you have a bit set to 0, it means nothing, it is to fill the blank. And then you have CR. What does CR stand for? The value CR plus 1 will give us the number of bits of color resolution. Okay, so this is the number of bits of color resolution. So as we studied, the pixel will have a value, and this value is an index in the lookup table. So the number of bits a pixel can have is represented by pixel plus 1, and the CR plus 1 is the number of of bits to represent a color resolution. It means inside the global color map, inside the lookup table. So if CR is for example 8, it means we have 8 bits for each color. And then we have M, which means if M equal to 1, this is 1 bit only. If M is equal to 1, this means the global color map will be following this descriptor. And if it is, of course, equal to 0, there is no global color map, only local color maps. We continue in the GIF format. If you want to open a GIF format, you now know how to read the bytes inside the GIF format in order to get the information. And after the screen descriptor, we get to the color map. The GIF color map is as simple as that. You have the red, green, blue, red, green, blue. So every three bytes are for an entry. So this is the red value for color index 0, followed by the green value, followed by the blue value. As we have already seen, CR plus 1 is the number of bits of color resolution, so maximum you can have 8 bits. So color map is set up in a very simple fashion as in figure 3.14. However, the actual length of the table is equals to 2 to the power pixel plus 1 as given in the screen descriptor. So we continue the image descriptor. After the color map, what do we have? After the color map, we have the image descriptor. So let's see how the image descriptor is structured. The image descriptor is structured as follows. First, between him and the color map, we have this byte. It is set to 0, 0, 1, 1, 0, 1, 0, 0. And this is an image separator character. This is a comma. Okay, and then we have 2 bytes for image left, 2 bytes for image top, 2 bytes for image width, and 2 bytes for image height. So you don't only use to know the width and height, but you have to know also the start of the image in pixels from the left side of the screen and the start from the top of the screen. So how much you have to move from the top left corner of the screen. and then you have the width and height, and then you have those pixels in this way. M is equal to 0. It means just use the global color map we gave you and ignore, this is an ignore pixel. If M is equal to 1, it means no, use our local color map, because of course we studied the color map and we know that sometimes it sets to best suit the content of the image, especially if we follow the median cut algorithm to generate it. So if M equal to 1, this means that you have to follow the color map, the local color map that is special for this image. I recall that a GIF format, the GIF file format, may contain more than one image in one file. And if I is equal to 0, it means that I is formatted in sequential order. You have to read it line by line. And if I is equal to 1, it means that the image is formatted in the interlaced order. So the first line I gave you, this is line 1, but the next line, I'm not giving the line 2, I'm giving the line 4, and so on. I'm giving you in the interlaced format for you to display it in an interlaced format as explained before. And then we have two bits to represent a value. This value plus 1, maximum 5. It means that this is the number of bits per pixel for this image. 4-pass interlaced display row order, in which order we are going to register the lines of the figure in the file format, and in which row accordingly they will be displayed. Along the GIF standard, we are going to make 4 passes. So it is only by 4 passes. The first pass I will code the line 0 and line 8. The second pass is divided into 2A, 2B. 2A will be dedicated for line 4 and for line 12. The third pass is for line 2, line 3, line 1, line 2, line 5, and line 10. As for the 4 pass, all the others that we didn't record in the first passes. As they arrive, they will be displayed in this order also. So first we will be displaying 1A and then 1B. So the user that is loading this image will be seeing the line 0 and 8 at the same time, and then next few milliseconds he will be seeing the ones that were sent in the second pass, and so on, and this is the interlacing. We can investigate how the file header works in practice by having a look at a particular GIF image. You simply can open a GIF image using an Unix, for example, the command od-c, for example, if the image is forestfire.gif, or head -2, and you can see the first 32 bytes interpreted as characters. We already explained now the first 32 bytes, so you will see the GIF signature, GIF87A, this is a signature, and then you have the bytes that follow. To decipher the remainder of the file header after the GIF87A, we use hexadecimal od-x forestfire.gif head -2 with a result. You can obtain the result of each byte, and you can transform each byte into binary in order to see every bit what does it mean. And this is again the same thing but in a simple presentation. This is what we would like to explain about the GIF format, and now we will have to mention quickly the JPEG format. The most important current standard for image compression is JPEG, of course, and because it takes advantage of the human vision system. It has some specific limitations. The human vision system has specific limitation. Our eyes are not perfect. We can see something and we can miss other things. And the JPEG is here to take advantage of this property, of this feature. The JPEG community said, if you can't if you can't even see, why should we code it and take place? So this is the main idea. So JPEG takes advantage to achieve high rates of compression, and the user set a desired level of quality. You can, as a user, set a desired level of quality. You can say, I want to code this image according to the JPEG standard with the quality ratio Q equal 10%, Q 100%. I want a very good quality, an acceptable quality, and so on. And we explained this in the chapter Introduction to Multimedia, the first one. And to remind the size of the original with a quality equal 10%, you can get a size which is only 1.5% of the original size. And with a quality, a very good acceptable quality, 75%, almost nobody will notice the difference in quality, but the size will be only 5.6% of the original one. Imagine how much you reduce the size without reducing the quality. And this here is the big importance of JPEG. By comparison with GIF, GIF compresses to 23%. It makes the compression of an uncompressed image. This is a JPEG image. Look at the quality of this image. This is a JPEG image with very low quality specified by user. You can see that this image is pixelized. So this is always forest fire, but a very bad quality JPEG. But as we said, if we choose this quality, it means we want a very, very high compression. So we judge that it is worth it. Portable network graphics came to supersede the GIF standard and extend it in important ways. Special features of the PNG file include support for up to 48 bits of color information, the double. This is a large increase. Files may contain gamma correction information for correct display on the screens according to each screen feature, and alpha channel information for users as control of transparency and others. And thirdly, a progressive display of pixels in a two-dimensional fashion. Show few pixels at a time over 7 passes through each 8 by 8 block of an image, not row by row. So we have enhancement. Already the GIF 89 had enhancement and delays in the progressive display and in the animation. So PNG came also to advance it. Another file format is the TIFF file format, which stands for Tagged Image File Format, and support for attachment of additional information tags provides a great deal of flexibility. You can add tags to image. The most important tag is a format signifier, what type of compression, etc. is in use in the stored image. TIFF can store many different types of image. Not only you can have one type of image, you can have 1-bit, grayscale, 8-bit color, 24-bit RGB, different types of image stored in this file format. And you can say which type you stored in this one. And TIFF was originally a lossless format, but now with a new JPEG tag, it allows one to opt for JPEG compression inside TIFF. So it is not a raw data anymore. If a photographer gave you TIFF, it's not automatically the raw data. Maybe it is a JPEG compression inside. The TIFF format developed by the Aldous Corporation in the 80s and later was supported by Microsoft. We arrive at graphic animation files and few dominant formats aimed at storing graphics animations, which are series of drawings or graphic illustrations, as opposed to video, which are a series of images. The difference is that the animations are less demanding of resources than videos. We mentioned the FLC is an animation of moving picture file format created by Animation Pro The FLI is similar also. The GL produces somewhat better quality moving pictures. The GL animation can also usually handle larger file size and many older formats as GL, Apple QuickTime files, and animated GIF 89 files. The PS and PDF file format, the PostScript is an important language for typesetting, and many high-end printers have a PostScript interpreter built. It is a vector-based picture language rather than a pixel-based, and the page element definition are essentially in terms of vectors. PostScript include text as well as vector structure graphics, and GL bitmapped image can be included in output file. Encapsulated PostScript files add some additional information for inclusion of PostScript files in another document. I'm just reading because it's self-explanatory, you can understand it, and just reading in case if there is a remark so I can explain. And PostScript page description language itself does not provide compression. In fact, PostScript files are just stored as ASCII. So we continue to finish this chapter. This was a very long chapter and I think we explained it in detail. A parallel PostScript Adobe system include LZW compression. We will be seeing the LZW compression in the next chapters, and it's portable document format, which is PDF file format. PDF files that do not include images have the same compression ratio 2:1 or 3:1 as file compressed with other LZW based compression tools, but with images the compression ratio will differ also. Some other file formats, you have also the Microsoft Windows, the WMF format, which is the native vector file format for the Microsoft Windows operating environment. So if you are on Paint and you want to save an image, it will propose to you the first. So just like Microsoft Windows format, the native vector file format for Microsoft, there is also another file format for Microsoft, which is the BMP, not the vector file format, but the major system standard graphic file format. And it is used also by the Microsoft Paint. And you have other file format like Paint and Pict for Macintosh. And Pict is a format that is used by Macro, which is a vector-based drawing program. And you have PPM, also a very known file format, the graphics format for X Windows systems. It supports 24 color bit maps and can be manipulated using many public domain graphic editors. And here we come to the end of our chapter 2. I hope it gives you an idea about the image representation. We made inside this lecture video small application on MATLAB, very small, in order to initialize you. And we will be doing other videos for applications, for dithering, for median cut, for image manipulation, resize, and etc.